Okay, let's go back to where we left off last time. Also, I realized I made it more complicated than I needed to because I asked you to do it in an acidic solution instead of a basic solution. So let's go back and talk through the example we left off on. So if you remember, we'd done this one 2 different ways. We went through and we split it because it's pretty simple to do that. We can split it, we saw that. And then I said, let's do it instead where we're leaving it together. The reason I wanted to do this one both ways is I realized when I taught this in the past, I always used the leave it together method for the really, really hard problems. And that's because you can. So since you can use it for the hard problems, that's what I was doing. Unfortunately, it gave everybody a false impression that this was like a super hard way of doing it. So that's why I want to do this one. Even though we can split it, I want to leave it together just to show you how it works. So let's go back and talk through it. So I'm going to block off some of it so that we don't have too much going on. So we had went through and we wrote all the oxidation numbers. Remember, that's like step 1, get good at that before you move on. And then we said, okay, what's happening with the electrons? When we leave them together, we deal with the electrons first, and then we take care of everything else, okay? That's the real big difference. And so we said, well, between here and here, we have 3 electrons being transferred. Between here and here, we only had 1. You have to have the same number of electrons, so we multiplied that whole little section, that half reaction, by 3. So we put this here, and we put this here. And we said, okay, well now we have 3 electrons going back and forth. This is it's a 2 to a 5, so is it being oxidized or reduced? Let's go other way. This is going from a 2 to a 1, so is it being oxidized or reduced? Reduced, right? It's going down in charge. So this is going from a 2 to a 5, so it's being oxidized. All right. So this one is gaining electrons or losing electrons? Losing electrons, right? Leo goes grr, loss of electrons is oxidation. Okay, so this one loses electrons, gives it to the copper. So it loses 3 electrons, give 3 electrons to the copper. All right, so that's all just review. Get you back on track, because the Thursday to Tuesday is a really long time for some reason. It just feels like a long time. All right, so then we said, okay, now we got my electrons balanced. Now all we have to worry about is, well, everything else. So let's take care of our oxygens and our hydrogens. This is where things are the exact same as the half reactions, except that you only have to do it once. So we went through and we added the waters. So we added 2 waters to balance the oxygens, right? Yeah, that messes up our hydrogens. We don't care. We can fix that later on. We're just worried about our oxygens right now. So that was what the 2 waters were. Then we said, okay, now we need to fix our hydrogens. So we added in 4 H pluses. And at that point, we're done. Last time I kept going by accident and went with the OH minuses, but we're in an acidic solution. We don't need to do that. So we can just stop right there. At that point, we're done. The only thing left to do is rewrite it. And take a glance back in your notes from last time, and you'll see that this is way shorter than the other way, especially because the only reason I even bothered writing this down here instead of writing it up here was for you guys, just for the sake of taking notes so you knew what order we did everything in. Otherwise, it would all be in one line. That's my little sales plug for leaving it together. There's going to be times where you have to leave it together, but there's a lot of times where it's not really that big of a deal. Just do it. And then you don't have to split it. You don't have to do the half reactions. There are times where the half reaction method is a little bit easier, so you may want to learn it anyways. That's up to you. Okay. Now let's do an example of a hard one where we are actually forced to leave it together. Okay? So this is one where trying to do it with a half reaction method, you might be able to pull it off, but it's really much, much simpler if you can just leave it all in one. Okay, first step, we always go through, for no matter what, we always go through and do our oxidation numbers. So here we have silver in its natural elemental form, so what is it? 0. Here we have hydrogen, sulfur, and oxygen. We'll leave the sulfur till last. What's the hydrogen? Each one? +1. And what's the oxygens? -2. So now we can do the sulfur. So we need to keep track of all the charges. So we have 8 negative charges, right? 2 times 4. So we have 8 negative charges. We have 2 positive charges. So overall, we're at a -6. And what do we need to be at when we're done? 0, because that's the charge, right? The charge on this whole thing is 0. So we need to make this whole thing equal to 0. So right now we have -6. So what does sulfur need to be? +6. All right. Same thing over here. Now we have to deal with the ion here. To do this, you really have to almost know what the sulfate ion's charge is. What is sulfate ion's charge as a group? -2. So what does that mean the silver is? +1. You may also have just known that silver was a +1. Sometimes, depending on the ion, you may have to still use the polyatomic ion's charge. This one you would have been okay. Oxygen is still, what is oxygen? Still -2. So now we look at this, we have a -8, we have a +2. So what is the sulfur here? It's still a +6. And I'll give you a hint. If you have the ion like this, like a polyatomic ion, and the whole polyatomic ion doesn't change, your oxidation numbers aren't going to either. Okay, now this one. Our oxygen's a -2 again. What does that make this sulfur? +4, right? Because there's 2. Good. Now, hopefully you can see why maybe we can't split this one. Because we have sulfurs doing 2 things. We have a sulfur going here. Is this sulfur doing anything from an oxidation standpoint or oxidation reduction standpoint? No. But this one is. And then we have our silver going here. All right. We still have to account for the sulfur that isn't being oxidized or reduced when it comes to balancing our elements. We just don't count it when it comes to balancing our electrons. And that's why it's kind of a jerk to try to split apart, because if you take these and you try to take this and put it over here, and you try to take this and put it over here, well, now you have a sulfur here. Where did it come from? So splitting it is just a pain. This isn't to say you absolutely couldn't do it. It's just not very easy. So let's instead leave it together. So first step, balance everything that isn't hydrogen and oxygen. So what do we need to add to the silver? And what do we need to add to the sulfur? How many do I have over here? 2. So what should I put here? 2. Okay. Now let's balance our electrons. Let's look at our silver first because I think it's a little easier. To go from a 0 to a 1, how many electrons are transferred? 1. And how many times are we doing it? Twice. So we have 2 electrons moving around in that situation. Now let's look at our sulfur. To go from here to here, is any electrons being exchanged? No. What about from here to here? How many? 2. Here's the part that people get a little tripped up on. How many times is it happening? Is it 2? It's 1. Why isn't it 2? You have 2 sulfurs here, but what is one of them doing? One of them is not doing anything. One of them is just staying as a sulfate. But one of them is going to the sulfur dioxide, right? So one's staying the same, one is changing. And so the one that's staying the same doesn't matter here. So it's just times 1. Okay. So now we balance our electrons. Well, that's convenient. Are they already balanced? Yeah, all done. So our electrons are all taken care of already. Those happen to work out nice for us. All right. So we'll just do a little check. The electrons are balanced. Just for the sake of notes later on. All right. Now we're back to waters to balance oxygen, hydrogens to balance hydrogen, and if needed, hydroxides. So we look at this whole thing. We have 8 waters over here. We have 8 oxygens over here. We have 4, 5, 6 over here. So what do we need to do? How many? 2 waters. Now we look at our hydrogens. We have how many over here? 4. And how many over here? 4. So do we need to do anything with hydrogens? Nope. Okay. And now, because of the way I wrote this, I do have to rewrite it. If you were doing this otherwise, you would have just put it up here, and you wouldn't have to rewrite. We double check to make sure that there's nothing on either side that needs to be canceled. There isn't. We double check to make sure there's no electrons floating around. There isn't. And so we are all set. Just for good practice, we should go through and talk about what is oxidized, what is reduced, what is the oxidizing agent, and what is the reducing agent, right? Good review. Okay, which thing here is being, let's start with reduced. What is being reduced? Which one is going down in charge? Sulfur. What does that mean? Which one's the oxidizing agent then? Yeah, the H2SO4. Typically, when we talk about something being oxidized or reduced, we talk about the element, and typically we talk about the oxidizing or reducing agent being the whole thing. I say typically because there's exceptions, but generally that's what we do. So which one is being oxidized then? Silver. So what does that make the silver then? And then one last thing. Should include our phases up here, so I'm going to go fix that real quick. So a note on phases here. When you're balancing these, like for yourself, and you're in all the in-between steps, but you can be lazy with the phases. That's fine. If you're doing all the in-between things, don't worry about it. But when you write your balanced reaction, you should make sure to go back in and put them all in. You definitely want those phases there in order to have a correctly balanced reaction. Okay. So you can always use this method, right? You're always allowed to use the leaving it together method. The half reaction method is sometimes more convenient. Not always, but sometimes. It's just that there's times like this where trying to use a half reaction method, not so good. So make sure you can at least do this one. I promise to put one on the exam that'll be a huge pain if you try to break it apart, but it'll work really nice and easy if you do it this way to help motivate you on that. Okay. So I'll do a few more examples of these and put them online. I don't quite have it done yet. I've been working on all the nuclear things. So that'll be up in a couple of days if you want more practice on that. Okay. So when we're balancing redox reactions, kind of a quick review, the reason these are different from the other reactions, okay, the reasons these are not the same as all the reactions that we've done up until now are because of that exchange of electrons. There's times where you could balance all of the atoms and everything would look like it was okay, but the electrons wouldn't be balanced, and so you'd get it wrong. So you always have to account for the electron balance somewhere. You can do it in the half reactions, or you can do it in the half reactions as a part of the whole like we did here. Either way is fine. So At minimum, you have to know how to do the leave it together way just because it always works, it's universal. It really is useful to know the half reaction way too. My personal favorite is always the leaving it together, but lots of students disagree with me on that and like the splitting it apart. So just make sure you can do both if that's what you want to do. All right, quick announcements. Don't forget to finish up your last part of 18. You should have it mostly done, but if you have a few left over, make sure you do those. If you need help with it, office hours right after class today. You're mastering for chapter 20, it's all one section, so it isn't actually due till Thursday, but you should at least go do all the redox reactions, knock them off, get them out of the way. You should be able to do a decent chunk of them. The last two homework assignments aren't quite as long because we are going a little faster through these sections, and I think that's perfectly okay to kind of skim the surface of these two sections a little bit more than the buffer section. So your homework reflects that, and the exam will reflect that too. I mentioned this before, my office hours next week and exam week are gonna be a little screwy because I'll be here on Tuesday for normal class, but I have to leave right after. So I'm gonna end up putting some office hours on Monday, a big chunk of them on Monday for you guys, and then after on Monday of exam week, I'll do the same thing. I just am waiting on a few different things to set the exact time. But just so you know, I will have extra office hours to make up for the time that I'm being forced to leave you guys. But we'll make up for it somehow. Just give me a few hours to figure out the timing. All of your podcasts from Nuclear Chem are up, so I finished the last few before class. So whenever you want to do that, go for it. It's about an hour and 20 minutes, just like class would be worth of podcast. It's just they're all broken down into section because uploading an hour and 20-minute video and watching it straight through is miserable. So it's all in little sections for you guys. So just watch it whenever you have time. It needs to be done by final exam time, obviously, but you can do it whenever you feel like it. Okay. And then last set of announcements, because we're approaching the, what I like to call end of the quarter freakout period, which is generally about the last week and a half of the quarter. I think the short winter break made that less bad because you guys are all just too tired to freak out, which I'm not sure if that's a good thing or a bad thing. But in any case, let's get some of these out of the way because I'm already starting to get questions on it. Okay, yeah. So this isn't the syllabus, but no one necessarily always reads it super carefully. You are allowed to drop a homework assignment. I just kind of keep it quiet up until now because I want it to be used for emergencies. So now that you only have 2 homework assignments left, you be aware of that. So if there was one homework assignment that just you didn't do so hot on, you get to drop it. If there is one assignment that you completely forgot about, don't worry about it, it's gone. Go back and do it anyways, go back and review it anyways for the sake of doing well in the final, but you can drop that so it won't hurt your score. Don't forget about the online extra credit assignment. If you're saying, I could probably use a little bit of a boost on my final grade, it's just going through and picking a few problems that you had trouble with on the exams and doing a little video. You can steal a friend and do like a tutoring session with them and videotape it. You can do your own kind of video podcast like I do, however you want to do it. So lots of details about that online. Details about the final exam I'll include on my next Monday weekly summary email. So a note on this though ahead of time. I did kind of structure this class a little differently than I have before, where we spent a lot more time on acid-base chemistry, buffers, and we're speeding a little bit through electrochem and nuclear chem. That's because it's the most important part for you guys to know. I want my biology researchers, I want my doctors, I want my pharmacists to understand buffers and acid-base chemistry really well. I don't want to go to lunch with all your junior and senior level lecturers and have them say, no, your students they don't know buffers. I don't want that. This is like the most important thing. And so I spent a lot of time on it. And therefore, electrochem, nuclear chem, they're not going to be as tough of problems. So quite frankly, you'll find that the electrochem and the nuclear chem, I'm going to pick the simpler sorts of problems for. I'm not going to try to get too tricky with it. So keep that in mind as you're studying and as you're looking at the homework and saying, she didn't give us very much homework on this, and they don't seem as tricky, and maybe she's just going to slam us on the final because she's mean. No, that's not the goal here. So I will put more details about the percentages, like what percentage is this, what percentage is that, once I write the exam. But just keep in mind the stuff that we spent the most time in on class, that's what's going to be focused on. And don't forget, yeah, as of right now, if I had to assign grades today, like end of the world happens and you still need your grade for whatever reason, it would be slightly curved. Of course, the final can always change that one way or another, but as of right now. Okay, questions on any of that? Perfect. Moving on then. All right, now we're gonna actually do something with all these reactions. Now we know what they are, we know how to balance them, we know how to work with them, we know we have to have one that's oxidized, we know we have to have one that's reduced. Now we're gonna actually figure out what we can do with them. And the first one are gonna be electrochemical cells. Okay? So our idea here is gonna be, first off, define it, what is it? We wanna be able to identify all the components of it. We want to identify which reaction is happening at which place. Like you should, if I brought a setup in here, by the end of this you want to be able to say, oh, I know what's happening right there. I know what's happening right there. And then define what, so like we're going to talk about electrodes, and we're going to want to know what's happening at the actual electrodes. Are we depositing something? Are we dissolving something? What's happening? And then our last thing, we'll talk about galvanic and electrolytic cells. We're gonna touch on the difference, we're gonna do the main definition of the difference today, like what actually defines each. And then probably next time, maybe this time, I don't know, we'll get to talking about electrolytic cells especially, because electrolytic cells are actually used very different than a galvanic cell, regardless of what the actual definitions are. So first off, what are these? So by definition, a galvanic cell is an electrochemical cell where a spontaneous chemical reaction is used to generate an electrical current. An electrolytic cell is the exact same thing, except it's a non-spontaneous reaction. All right. So we're allowing a chemical reaction to happen. The transfer of electrons are going to take place in a way that we can use them for a galvanic cell. For an electrolytic cell, we're going to have to put energy in. An electrolytic cell doesn't go on its own. It's non-spontaneous. We have to hook something up and force it to go in that direction. I know I talked about this last time, but once again, oxidation is always going to happen at the anode. Reduction is always going to happen at the cathode. That doesn't matter whether it's an electrolytic or a galvanic cell, okay? Which one is the anode will switch. Like if you have a galvanic cell and then you hook up a battery and run it in the reverse direction, where the anode is will switch, but the anode is still oxidation. The cathode is still reduction. And the memory trick for that is red cat and ox. Not a particularly amazing memory trick, but that's what it is. Okay. So right here, I have an example of a spontaneous one for you. We haven't talked about how to figure out which one's the anode and which one's the cathode yet, so don't worry about that. We'll cover it in a second. But so if this is happening, I'm just going to tell you that this is the anode and this is the cathode so that we can talk about it. This reaction right here is happening over here. This reaction right here is happening over here. So over here, our copper sulfate solution is going from a solution into a solid. Over here, we have our zinc solid, which is going into zinc 2+. Okay? So we have these different things happening. Now, besides just, okay, there's something happening at this electrode, there's something happening at this electrode, things are happening in between the two. So first off, which one is giving up electrons? Which one is losing electrons here? So which one has electrons as a product? Zinc, right? It's losing its electrons. It's the anode. It's the oxidation. So the electrons over here that are released from this go through the wire They do whatever we want them to do. Maybe they read a voltmeter, maybe they light up a light bulb, maybe they run an MP3 player, they do something. And then they come over here. And once they come over here, now those 2 electrons are used to turn copper 2+ into copper solid. All right, so that's what the wire is for. The wire lets the electrons go from one place to the next. Now there's a problem here. If we do that and we don't do anything else, if all we have are these electrodes in this wire, over in this solution, we are making +2 ions. Yeah? Over in this solution, we're destroying +2 ions. But they're in solution, and a solution has to be neutral. You can't have more plus charges in a solution than you have negative charges. And so we have to balance that somehow. That's what the salt bridge is for. The salt bridge is like, everyone kind of just, oh yeah, you just stick a salt bridge in there. But don't forget what it's actually used for. It balances those ions. So as this thing is happening, as all of these electrons are moving around, and we're taking this from a solid to an ion, and we're taking this from an ion to a solid, the salt bridge is what allows counter ions to move into solution. So you put something in the salt bridge that isn't going to really react. Usually it's like sodium chloride or something like that. And it's just something that allows ions to move back and forth to balance the solution. Okay. So we have our anode, we have our cathode, we have our salt bridge, which allows the flow of ions. We have our wire that allows the flow of electrons, and we have probably something here to do something, whether it's voltmeter, light, something. If this were an electrolytic cell, you would need a battery there to run it backwards, or some sort of other power source. All right, so let's answer some questions. I'll throw each one up and then give you a few seconds to think about it. Where is the metal deposited? So give it a little bit of thought before saying it. I'll let the people, or if you have the answer already, give the people around you a minute to think about it. And remember, in this case, I'm just telling you that this is what is happening at each place, right? We'll get into how we figure that out in a minute. Okay. Where is the metal deposited? So we really have 2 options. We have the copper electrode and we have the zinc electrode. So what do we think? Count of 3. 1, 2, 3. That was really enthusiastic, but right. So yeah, copper. So that's on our copper, right? How do we know that? It's a product. We have the solid as a product. Over here, the solid's a reactant, and it's going to an ion. Which way do the electrons flow? This one's actually a really generic question. We can kind of always answer this. The electrons are always going to flow from either the anode to the cathode or the cathode to the anode. So let's think about it. Which one is losing electrons, the anode or the cathode? So loss of electrons is oxidation, right? Leo, the lion goes grr. Loss of electrons is oxidation. So that is the anode. Loss of electrons is oxidation. That happens at the anode. That one is giving up the electrons and it's going to the cathode. So it's always going to run anode to cathode by definition. So say it one more time. Loss of electrons is oxidation, right? Leo the lion goes grr. So that happens at your anode. So it's going to go from your anode to your cathode. So in this case, from here to here. Why do I separate the reaction? Why do I keep them in separate things? If I just threw this all in a pot, would it work? If I just dumped all this in a solution, would it work? It would actually. Well, assuming you had the right concentrations of everything. But assuming you set it up properly, you get a reaction. Could you run anything from that reaction? Well, can you just stick an MP3 player in a vat of ionic solution with some metal and see if it works? All right, pull out your MP3 players and try it. Is this something you guys want to do? Absolutely not, right? It's not going to work. There's no way that that's going to work. One, because MP3 players don't do well in water. Two, because those electrons are going to just go from one ion to another. They're not separated by anything. The idea with putting it in a galvanic cell is you keep them separated. You keep them apart. So the electrons have to go from here to here. They have to go through a wire, and then they can be used to do useful things. How we end up separating them really varies a lot depending on the situation. Obviously, in a battery, you can't separate these in two different little cells like this. There's a variety of ways that the separation occurs. Okay, and we already talked about this one. Why is the salt bridge necessary? It allows that flow of anions and cations. It allows the flow of counter ions. We're making ions on one, we're destroying ions on the other, not destroying them, but converting them into a metal. We need to make sure that our solutions are still balanced, that our solutions still have the same number of plus charges as they do minus charges. Okay? So if you look at this side, we're destroying positive ions and turning them in to copper solid. We're making the solution less positive. So it's going to pull positive ions from the salt bridge. Over here, we're putting positive ions into solution. We're making it more positive. And so it's going to pull negative ions into solution to counter that. Okay. So last quick review before moving on. We have our galvanic cells. We usually keep them in separate reactions when we're doing galvanic cells. Electrolytic cells will be a little bit different here. For galvanic cells, we almost always keep them in separate containers or in some other way separated so that we can get work out of it. That's the only reason really for separating it. We need to get that work out of it. This allows the electrons to flow from one area to another, and that's what allows us to do chemical work. Without that, it's just switching electrons in solution. We don't get any work from that. Given the reactions at this point, you guys should be able to identify the anode and cathode. You look at which one's producing electrons. That one is losing electrons. That is your oxidation, so that is your anode. Okay, all that's great, but if I don't give you the reactions, or more specifically, I just throw a couple of half reactions at you, how do you know which one's which? How do you know which one is oxidation? How do you know which one is reduction? And for that matter, how do we know how much energy we can actually get out of the whole thing, right? That's what we're going to do in the next section. So to do all of that, we need something called cell voltage. And it's very similar going along with that is reduction potentials, which is going to let us calculate the cell voltage. So in this section, what we'll talk about, we'll go through and we'll define what cell voltage is. You may already have kind of a hint because we use this in common everyday language. But we'll talk about how that relates to reduction potentials, how to decide if a given cell is spontaneous or non-spontaneous, right? Like if I just give you a reaction that's happening, you should be able to decide if it's spontaneous or not. And then if I just say, okay, put together a cell with these materials, which way is going to be spontaneous? What's going to be happening? Those are all the things we're going to figure out. So first off, something called electromotive force, which is not at all a force. It's actually a voltage. It's just colloquially what it's called. This is going to be synonymous with something called cell voltage. This is what, if you run one of these galvanic cells and you measure the voltage, what you'll get off it. Now, these cell voltages are going to come from an addition of the half reactions voltages. So we have for each half reaction a reduction potential, or if it's being oxidized, an oxidation potential. And when we add those up, that's what the cell voltage is. So the further apart they are, the higher the cell voltage. So if you want a high cell voltage, you want one thing that's really, really good at being reduced. And you want one thing that's really, really good at being oxidized. And that's what you make your cell out of. If you have like one thing that's sort of kind of wants to be reduced, and you have one thing that sort of kind of wants to be oxidized, you'll have a much smaller cell voltage. Okay? When you look these up in tables, they're listed as reduction potentials. Okay? So if you just see an E naught with no subscript, I try to be really consistent on my notes with writing reduction or oxidation as a subscript, but if you ever see it without one, that's a reduction potential, okay? By just convention, it's always listed as reduction potential. This is a random smattering of them. This is obviously not all of them. And of course, any of these that you would need, you're always given. On homework, you have to look them up, but on the exam, they'd be given. Okay. Let's talk about how to go from a reduction potential to an oxidation potential. We generally talk about things in reduction potentials the most, but sometimes it is useful to talk about an oxidation potential. And this is really, really, really complicated. Ready? You make it a negative. That's it. That's all there is to it. Okay? So if you have a reduction potential and you want to know, well, what's the cell voltage of the flipped version of that, of the oxidation? Put a negative charge in front of it. You're done. That's relatively important when we actually go to start calculating these. I'm going to teach you two ways to do it because it's a complete 50-50 split on what people like. And this comes back there. The table's listed at 1 molar, so standard values. Just like most table things, you have to have a standard that you list everything at. If you change the concentrations, you change the voltage. So these are all standard, and unless stated otherwise, you can always assume that what I'm asking you is at standard. There are some times where we have gases. That's at 1 atmosphere. So if you look here, there should be at 0 hydrogen. That's a gas, so that's just at 1 atmosphere. All right. So our EMF or our cell voltage, whichever phrasing you like better, they're synonymous, is going to be the difference between these, right? It's going to be the difference between our reduction and our oxidation half reactions. So you can think of it as a difference between the reduction potentials, or you can think of it as adding the reduction plus the oxidation. Before we do examples with these, there's one thing we need to talk about on where these numbers come from. We cannot hook up half of a reaction and say, let's measure the voltage. It doesn't work because nothing happens. You have to have a whole cell in order to make this happen, which means that all of these have to be measured against something. We have to pick something and make that thing 0. So they've done this, and you can see it from the table which one they've picked. They pick hydrogen. And they say that this is 0. Okay? That's just by definition, chemists decided that a long time ago. And then everything else is measured against that. So that's called the standard hydrogen electrode. You'll sometimes see it as capital S, capital H, capital E. And what that does is it gives us something to measure everything else against. So every voltage you saw listed there was as if you took that half cell, hooked it up to this, and then measured it. Okay? So everything here is relative. This is the one and only cell voltage that you would be expected to memorize because it's 0. And it's important to know that that's what we measure everything else against. It's also important to know that we measure everything against something, right? We don't just throw a half cell and say, magic, happen. We have to hook it up to something. Something I want to point out here, and it's not just for the standard hydrogen electrode. It happens pretty much any time that you have a gas, and a couple of other times too. We have a platinum electrode here. So I switched pictures at the last minute. Go ahead and write on this electrode platinum, PT. And to switch pictures due to copyright issues. So just add in a little, oh, it is there. It's just not showing up on mine. OK, if you can't see that, it does say PT on the electrode. Why do we need that? Why do we have a platinum electrode if we're having a hydrogen reaction? Platinum has one really important characteristic. Anyone know what it is? It doesn't react with things. It's one of the reasons why platinum jewelry is expensive, besides just it's shiny. It doesn't react with anything, it's very stable. Now, when we're drawing pretty pictures, we just throw platinum up there because we're not worried about cost. So who cares? There are other things that you can use. Certain cells you can use like palladium. You can use graphite for some cells. So if you ever see an electrode and it seems kind of random, like it's not doing anything, or that's what's going on. It's what we call inert. It's not reacting, okay? So we can always use platinum, except when it comes to real life. Platinum's really, really expensive. So when I was an undergrad, I worked for a company, and we used to need inert dishes. And one of the guys comes running into the lab one day, and he says, have you seen a dish? It's about this big. It looks dingy and dirty and gross, and it's $10,000. Platinum's expensive. It's why we don't give it to you in lab, sorry. You would not want those lab fees. Okay. So we just need an inert metal to conduct electrons. Again, you will see other ones. Palladium and graphite, I think, are the two that we kind of throw at you guys occasionally, but you'll see it here and there. Okay, so now we have our reduction potentials. We know where they came from. We know they're not just numbers on a table. We measure these reactions against the standard hydrogen electrode. Now let's figure out how we actually use them to calculate cell voltages. This is one of those where there's two methods. Pick the one that seems the most intuitive to you, and then during the other half, just put on your earmuffs and don't listen, okay? Like, you know, little kid earmuffs. Yeah. Okay. So and the reason why it's really important not to mix these up is if you do both, if you try to combine them, you'll get the wrong answer. It's one or the other. So in the first case, what you do is you take the reduction potentials. You take the numbers straight off the table and you don't do anything else to them, okay? And then you do you do cathode minus anode, okay? You figure out which one's your cathode, you figure out which one's your anode, you do cathode minus anode. Numbers from the table, do not adjust, do not change sign, just do that, okay? So that's one option. You have to remember here, you have to be able to figure out which one's your cathode, you have to be able to figure out which one's your anode. So you do need to remember that oxidation occurs at the anode, reduction occurs at the cathode. If you continually mess that up, like no matter how many times you say it to yourself, you mess up which one's the anode and which one's the cathode, this is probably not your method. The other way, this is my personal favorite, but you shouldn't let that sway you. It's not because it's better, it's just because I like it, is instead to do addition. And notice what's down here now. This isn't reduction, this is oxidation. What do we know about the oxidation potential? Is it what's listed on the table? That's the reduction potential. How do you take the reduction potential and turn it into the oxidation potential? You make it a negative, okay? I like doing this way because honestly, when I was a freshman taking this class, I just didn't want to memorize something like what the name of the anode was and what happened there. I also like this way because you don't have to remember which one goes in which direction. That being said, if you're pretty good at remembering things, don't worry about it. You can do the first one, that's fine. Just don't do both. Pick one, stick with it. So these are both from the table. Probably want to write that next to it. Both table values. In this case, this is from the table, and this is the negative value of what's in the table. Okay? Now, of course, why are these the same thing? It's not like it's a whole different way of problem solving, right? It's just taking this into account. This way works that into the equation. It says, oh, okay, reduction of the cathode, and then this is the oxidation potential. It's the negative of the anode. So they're identical in every way except the actual what numbers you plug in and what you have to remember. All right, so let's do these. So first off, I say calculate the cell voltage for a spontaneous zinc 2+, copper 2+ cell. Notice I didn't give you the half reactions this time. I just say, okay, here we go. Here's the things we're going to use. What's the cell voltage? So we need to decide which one's the anode and which one's the cathode first off, okay? It's kind of step one. What is happening at which place? I say that it's spontaneous. So this is important and probably deserves a few circles and stars. E cell positive is a spontaneous reaction, okay? So if you want something to be spontaneous, you need to make sure that the voltage is positive. If the voltage is negative, that means you're going to have to put in that voltage to make it happen. So for any time I list spontaneous, what I'm telling you is make E cell positive. So of course then non-spontaneous is negative. So the way you kind of think through this is up to you. But basically when you take those two numbers and you add them together, or you subtract them, whichever way you're thinking of it, you need to make sure that the overall result is positive. So if you're thinking about it as filling into the equation, you need to fill it in a way that the E cell is going to be positive. Went out of order, sorry about that. But so in this case, here are my reduction potentials, okay? This is my reduction potential for my copper. This is my reduction potential for my zinc. So let's work through the logic on how you do this. Ignore the answers for right now. So let's work through the logic on how you want to think about it. So, logic 1, if you put your reduction minus your reduction value, right, this is saying table values, we need to make sure that overall this is going to be a positive number. So if you fill in 0.34 minus a negative 0.44, you get a positive number. If you do this the other direction, if you tried filling in a negative 0.44 minus a positive 0.34, you get a negative number. And you know, okay, mess that up. So do it by looking at it or do it by filling it in and realizing that nope, it's the other direction. Either way is fine. This is the other reason I prefer the second method, is to me it's a lot easier to see, okay, well if I'm going to flip-flop the sign and add it, which one's going to give me a positive number? Well, my 0.34 is already positive, and my 0.44 is negative. So I want to flip the sign of my 0.44. And then that's going to be 0.78. Since I flipped the sign of my 0.44, I know that my zinc has to be my oxidation. Whichever one you flip the sign of is your oxidation. Or whichever one you do the minus of in the logic 1 is your oxidation. Okay? So you almost end up kind of, to figure out which one is your anode and which one is your cathode, you basically end up calculating the cell potential to do it. You end up having to look at that equation or that logic, that idea of saying how these are going to add up, what's the difference between them. And you use that to decide which one's your anode and which one's your cathode. Okay, let's do another one. Here I say it's a little cut off. It looks like that's a 2 on the manganese. It doesn't matter too much, but just so you have it. In a typical alkaline battery, it has the following half reactions. Now, I told you something by telling you it's a battery. Is it spontaneous or non-spontaneous? Do we get energy from a battery or do we put energy in? We get energy, right? Unless you're recharging it, in which case, different situation. But we're assuming we're using the battery for power. So it's a spontaneous reaction. If we had to put power into a battery, that would kind of defeat the purpose, right? So by telling you it's a battery, I'm telling you it's spontaneous. And I gave you the half reactions. So now we need to think through and say, okay, which one is going to flip places? And if we look at this, and and one of these has to change sign or be subtracted, are we going to want to change the sign of the negative one or the positive one? We want it to be positive or negative overall? Overall, we want it to be positive, right? We want it to be spontaneous. A positive E cell is spontaneous. So when we add these together, we want to flip the sign of the negative one, which means that this one has to be your anode. Whichever one's sign flips or whichever one is your subtraction, that's your anode. So again, whichever logic you like better, pick the one that seems most intuitive to you. You say, okay, well, the one that's going to be subtracted, I need to subtract a negative to make this work. Or which one am I going to flip sign and then add to get a positive? Whichever logic you like. The other way you can think of it, think about the word reduction potential. If you have a very high potential to get a good grade in this class, are you likely to get a good grade or not? Yeah. So if something has a high reduction potential, is it likely to be reduced? Yeah. The word potential doesn't change meaning just because we're talking about chemistry. That would be really mean if the chemists were like, we're just going to change all the meanings of all the words. So because of that, we can use that to think of it too, right? We can say, well, which one has the higher reduction potential? That one will be reduced. In this case, which one has the higher reduction potential? Permanganate, right? And so because that MnO2 has the higher reduction potential, we know that that'll be our cathode. And our one with our lowest reduction potential will be our anode. So 3 different ways to basically do the exact same thing, whichever you like. Okay. Quick review of this section. So our cell voltages are always going to be calculated as our difference in potential energy between the anode and the cathode. All right? So the way that's phrased is really general. Our differences in potential energy between anode and cathode. What does that mean? Well, you either take the subtraction of your cathode minus your reduction potential of your anode, or if you want to think of it as plus your oxidation value, you just have to flip the sign. A spontaneous cell is going to have a positive E cell. That's called galvanic, right? We name that galvanic cells. And then our electrolytic cells, or our non-spontaneous reactions, are going to have a negative E cell. So you want to make sure you remember that. Positive is spontaneous, negative is non-spontaneous. It's opposite of Gibbs free energy. Okay. Now, knowing all that, we want to see which things are going to react with each other. Looking at just a general table of all these reduction potentials, what things can we combine to have some sort of reaction, whether that be spontaneous or non-spontaneous? What can we actually do? So we're going to take a little subset of the table, and we're going to play around with it a bit and decide, using the reduction potentials, what can you combine to react? Now, of course, in real life, there's always going to be issues with how can you actually make this work, what container can you put it in, what size, how expensive is it? There's a lot of sort of engineering aspects to this that get much more complicated very, very quickly. We're not going into that. We're going to stick with, given these reactions, what happens? On a lab bench, what happens? And we'll leave the rest for your engineering classes if that is your area of expertise. Okay, so here's like the rule, if you want to think of it. I'm not a giant fan of these types of memorization rules, but it is a little bit useful. So given that this is listed high to low, so high reduction potential to low reduction potential, the species on the left will react with a species on the right that is lower than it. So in other words, you could take chromate and react it with bromide. You could take OCl and react it with iron 2+. You could take copper 2+ and react it with tin 2+. Okay? Anything over on this side could be reacted with something lower than it over here. You're saying, why does it always have to be on the other side? Why does one of the reactants have to react with the other one's product? Well, don't forget, you always have to have one being oxidized and one being reduced. So one of the half reactions has to flip. Okay, that's a nice little rule. Let's think about why that is, though, so it's not just like a random thing that I told you. Up here, you have things that are easily reduced. Okay? And you know that because it has a high reduction potential. Again, if you have a great potential for something, you are likely to do it. If this has a high reduction potential, it is likely to be reduced. Now, these half reactions are all written as reductions, okay? They're written as reduction reactions, and this is why they are reduction potentials. When we go to decide, okay, well, what will this react with, you need something that is easily oxidized. And the things that are easily oxidized are going to be way down here. Because if you think about what this table means down here, it means that this does not want to be reduced at all. This lithium plus doesn't really want to go to lithium. What you'll actually find then is that these are easily oxidized on this side. It's just the reaction flips because you're being oxidized. So lithium solid is very, very easily oxidized. Lithium plus does not want to be reduced. Okay. Now let's do a couple of specifics. To do specifics, this is a really big table, so I'm just going to pull a subset of it out for us to work with. So I've just pulled a random subset out. If you're taking notes by hand, this might be a time to just say, go pull this off the internet, rather than try to write them all down. So let's figure out which one's the most easily oxidized, what's the best oxidizing agents, best reducing agents, and then give some spontaneous and non-spontaneous combinations. The diagonal rule is for spontaneous, right? It's what's going to happen if it's just on its own. Okay, so first off, these are easily reduced up here. These are not easily reduced, yeah? So maybe you want to draw an arrow, maybe you want to put not, however you want to do it to denote it to yourself. Easily reduced, not easily reduced. Now question, is zinc 2+ easily oxidized? That one is a trick question. I generally try not to ask trick questions, but that one's definitely a trick question. Is zinc 2+ easily oxidized? What is easily oxidized? Zinc solid, right? Zinc 2+ is already the oxidized form. So make sure you recognize that the easily oxidized part refers to the products. It refers to this because the oxidation reaction is flip-flopped. That's one of those really commonly confused things. Make sure you recognize it's the zinc solid that is easily oxidized. Zinc 2+ already oxidized. Same thing with nickel. Nickel solid is relatively easily oxidized. Nickel 2+ already oxidized. That's not going to be oxidized further. So just be careful with that. Okay. What does that mean about chloride and silver then? Or I'm sorry, the chloride dioxide and silver then. What does that mean about are they good reducing agents or are they good oxidizing agents? So they like being reduced, so they are good oxidizing agents. Good. So now I'm going to ask this in a little bit of reverse. What is the best reducing agent here? Zinc, just zinc on its own, or zinc 2+? Zinc solid, good. Zinc solid and nickel solid here. They're easily oxidized, so they're your reducing agents, okay? So the things that are easily oxidized are your reducing agents. Okay. Now let's write a spontaneous reaction. So we need to pick some things. Doesn't really matter which one. Let's just pick the first two. So if we take this one, if we take the ClO2, this is the most easily reduced on the entire table. And we want to react it with something that'll make a spontaneous reaction. Well, we could actually pick anything, because this is easily reduced, so anything on this side will react with it. So in this case, I'm going to pick the ClO2 and the silver as my spontaneous. So this makes my chlorite and my Ag. To figure out my cell voltage, I leave this one alone. I leave it at 0.95. And then either, depending on how you want to think about it, you subtract 0.8 or you add a negative 0.8. And either way, you get 0.15. Now, take a second and see if you can work out the non-spontaneous version. So that we all are on the same page, I picked two of them for you. But work out the cell voltage for the non-spontaneous one. Be like 20, 30 seconds, something like that. So I've started you off with the 2, and you work out the rest. Now slowly fill in as you go along, as I think you're okay. Don't wait for me. I'm waiting for you guys. And you found the cell voltage too, right? Cell voltage you have to be careful on. So you need to make sure you flip-flop the right one. Which one, so let's do this in the way that works best as kind of a blended way. Which one is going to be our cathode for the non-spontaneous one? Is it the zinc or is it the nickel? It's the zinc. So this one we fill in as is. You fill that one as is with the negative. Okay? You don't flip-flop it. Now, depending on how you want to think of it, because you have some options, I'm going to stick with what I did above. So I'm going to do the plus version. Which would one flip sign then? Nickel. So this one is going to end up being filled in as a positive. Or you can think of it as minus a negative, either way. So now when you get done, what's the sign of this whole thing? Is it negative or positive? It's negative. And if that isn't true, and I asked you for a non-spontaneous reaction, or in other words, I asked you for an electrolytic cell, or I said something like recharging a battery, anything like that that says, hey, we're putting energy into this thing, then you know you did something wrong. But in this case, we're fine. We're a negative. And so we know we're okay. Now, those are just two. Good practice is to go home and do this like 5 more times with each reaction, because you can come up with a whole bunch of other ones. So keep in mind the diagonal rule kind of works, but also be able to explain it. Be able to say, oh, that's because things with a high reduction potential are easily reduced. Things with a low reduction potential are not easily reduced, and so the oxidation is more likely to happen. Okay? All right. And the other thing to watch out for with the diagonal rule, and again, why I'm not a huge fan of them, I teach it just because it's how the book does it and people do like those sorts of rules. Make sure that the table is listed high to low. That diagonal rule being this direction only works if the table is high to low. So keep that in mind as you're using sources that is not your book to be aware of it. And that's because otherwise your low reduction potentials are at the top. So just make sure you're careful about that. To make sure that you guys understand the concept and that you're not just pulling random things randomly, I don't list your reduction potentials in order at all. You have to be able to figure it out from the actual numbers. Okay. So, back a long time ago, we taught you guys line structures. It doesn't really have anything to do with cell notation. But the idea behind line structures was, hey, you're going to be dealing with these big molecules in organic chemistry, and they're going to get annoying to write because you're going to have to write all these hydrogens, and you're going to have to write all these things, and it gets big and annoying. And so we're going to give you an easier way of drawing big structures. And sure, there's a learning curve to get over. You have to learn how to do it. But once you get the hang of it, it makes life next year a lot easier. Cell notation is the same sort of situation. It's a way for electrochemists to be able to quickly convey what is happening in their cell in a quick way without dealing with all these pesky, balancing reactions or various other annoyances that, they don't want to deal with. And that's fine, because it's not super important. And in cell notation, you can put all the important things that you need to know exactly what is happening in a cell without having to worry about balancing things, without having to write out this full redox reaction. And it's actually really easy to understand. Once you get the hang of it, it's almost like a mini picture of what's happening in the cell, just in one nice little text line. And so the idea with cell notation is to do that, to break down these reactions and just snapshot them in a way that's quick and easy to understand. Just by looking at it real quick. So we'll talk about what cell notation is and then do some examples of them. All right. So first one I just have written out for you, and we're going to walk through it. So we're back to our zinc copper cell, because this is like the standard one that we always use for explaining things. And this up here is what we call either a cell diagram or cell notation. You'll see either one of them used. Now, you always start with your anode, and you end with your cathode, okay? So you're always going to be, when you're writing your cell notation, working from anode to cathode, which is nice. That's also the way electrons flow, so that's useful. It's the same thing. You can remember that. Now, some rules. Single lines denote a phase change. So whenever you come across a single line, you know that something changed phase. If something didn't change phase, if you're doing something like a copper 2+ to a copper 1+, just something that happens, then there's no single line. Just use a comma. Now, when you hit the salt bridge, that gets a double line, okay? And then we're basically just kind of like drawing out a little mini picture. So if we start over here with our anode, we've already kind of been through why we know that zinc is the anode here. We've been using this as our example all along. You start here. You start at your anode, at the electrode, and you write zinc solid. And then you end up in solution. And in that solution is zinc 2+. And so you put zinc 2+. Now, do you have to write the sulfate? If you write the sulfate, it's fine. If you were doing some sort of situation where it was important to know what that counterion was, maybe zinc sulfate worked but zinc chloride didn't for some reason, then sure, write it. If you're doing something where that doesn't matter very much, then don't. The point of cell notation is to be useful rather than to be some sort of dogmatic thing that you have to do the same way every single time. Generally, not always, but generally you will write in parentheses, the concentration. If it's 1 molar or 1 atmosphere, you don't have to. If it's something else, you probably should. So if you're given a concentration, it's a good idea to stick it in there. So we went from our electrode into our solution. Now we hit our salt bridge, and so we draw a double line. It was only a single line between here and here because that was a phase change. But now we hit our salt bridge, and now we're into our cathode. We come over here, we go through our salt bridge into our cathode, and the first thing we hit is our copper ions. And so we put our copper ions. Make sure your phases are there, those are important. And then at the point that we hit our copper ions, we go back to our copper electrodes. And so we're back to copper solid with a line there. Every time you hit a phase change, you draw a line. Every time you hit the salt bridge, you draw a double line. And really the goal of this is to make this easier. Because if you want to write this whole thing out as a reaction happening, you have to balance the whole thing. And a lot of times that just doesn't really matter. Or if it does matter, we know that as chemists, whoever is reading our paper can balance the reaction for themselves. If they're reading our electrochemistry paper, they can handle that. And so this is just a faster way of getting information across. All right, so let's do another example. This time we'll do zinc with a platinum hydrogen electrode. Okay? It's a little bit different because it's a hydrogen electrode. So we start with our anode, we start with our zinc. In this case, I did tell you that zinc is the anode. Otherwise, we could go calculate it, but. So we come over here, and our first thing is our zinc solid. All right? Now, we hit a phase change, and we go into solution. And when we hit that phase change into solution, we draw a line, and then we draw our zinc 2+. If we wanted to write zinc sulfate, we could. We don't have to. And then we go through our salt bridge. So we draw a double line, and then we're into our 1 molar HCl. And so we go ahead and put our 1H+. If you wanted to put the Cl, you could. A lot of times you just put the ions that matter. Now we're into this little glass bubble that's holding our electrode into this solution, right? Because hydrogen's a gas. You can't just kind of bubble it in. You have to have something containing it. And so this actually will vary a little bit depending on the source. I'm not going to be particularly picky about it. You absolutely have to have this single line. Okay? That single line is required. And I think by definition that this single line you should put 2. You will sometimes see it written without it though. So you come through here, your electrons exchange with your hydrogen, and then you hit your platinum electrode. Just a nice little snapshot of the cell. You can see why they call it a cell diagram or a cell notation, because it really is just kind of a little picture. Okay. So let's do one big example where we walk through everything. So this is just kind of a, let's take all of electrochemistry that we've learned so far and combine it into one thing. So we have our standard reduction potential of a zinc electrode. I tell you what it is. Of course, you can always look it up if I don't tell you. Given that the standard potential of the cell where zinc is oxidized and tin is reduced, I tell you that reduction potential. Oh, I'm sorry, I tell you the combinations reaction. So I do switch things up on you a little bit. I tell you the cell voltage and I tell you 1/2 reaction. And you might be saying, well, yeah, but I could go look up the other one. Okay, sure, but I could definitely put it at non-standard reaction so you couldn't do that. So we're just doing it backwards for practice. All right. So I tell you that zinc is oxidized, which means that that's our reduction potential, right? So we need to be careful depending on how you want to think about it. Either tin's going to be, or zinc is going to be the one that's subtracted, or zinc is going to be the one that flips signs, whichever you want to think about it. So this is our reduction version. And I'm going to go ahead and write it flip-flopped as well. I'm going to just write our oxidation real big there so you make sure you recognize that that's me having already flip-flopped it. That's me having already changed sign. Now, that means that if zinc is oxidized, what has to be true about tin? Is it being oxidized or reduced? It's got to be reduced. And we don't know what the reduction potential is. However, what we do know is if we take this thing that we don't know, and we add that in. So I'm going to write this as plus 0.76. If you're doing it the other way, write it as a negative minus, or I'm sorry, a minus a negative 0.76 if you're doing it the other way. We know that that is equal to 0.91 volts. Oh, okay. Well, we know what they add up to, and so now we can solve for this. Right? So we can take our 0.91, we can minus our 0.76. Right, so I just subtracted that from both sides. Okay. Now I also asked you to write the cell diagram, so we'll do that real quickly. We know that which one is our anode? Zinc or tin? Zinc. So zinc is going to be oxidized. So we start with our zinc solid, we start with our zinc electrode, and mentally walk through the picture here. We go from our zinc solid into our solution. So we do a phase change. They didn't tell us the concentrations here. They're going to be standard, but because of that, we can just leave it. We don't have to write those. And then we hit our salt bridge. And then we keep walking through this imaginary picture of our cell. And now we're in the other beaker, and we're in the other solution. And both of our ions are in that other solution. And so they both go here. No phase change, no line. But now we have to have an electrode, and so we draw a line, and we put our favorite inner electrode. Because it's free, I'm going to go with platinum. Okay? So that's how you deal with a situation where you have two aqueous solutions. And this is how you deal with a solution where I'm asking you for a half cell instead of a whole cell, because I gave that to you. So just a couple of tweaks on things we've already done.